Okay. Thank you everyone for joining us today. We have two talks today for the GCSP seminar. Our first talk is with Carl Fields. He's a finishing grad student at Michigan State University. Carl primarily works on 3D numerical simulations of the final minutes of massive stars. Another thing is like I said, Carl's finishing this year. He also received the Price Prize this year from Ohio State University, and is also an NSF fellow. So I'll let you go ahead, Carl. Thanks.
Thank you. Let me get my screen over. Oh, no spoilers. Okay, can everyone see that okay?
Mm-hmm.
Awesome. Okay. Thank you for introducing me today and inviting me out to share my work. I'm going to be talking a little bit about some work I've been doing, like Anna said, on the last minutes of 3D simulations of massive stars. And I'm also going to talk about how we're using these 3D simulations as input for core collapse supernova explosions and the implications that those have for multi-messenger astronomy. Starting off, I wanted to give a brief overview of what I'm going to be talking about today. So I'll start off with the introduction, kind of bring us up to speed with core collapse supernovae. I'll introduce what I call a problem in our field in terms of their simulations, and then some potential solutions for solving that. One of those potential solutions that I'll go into detail about is the 3D progenitors that I'll present, and then after that, I'll talk about some ongoing work that we're doing looking at different initial progenitors of 3D simulations, as well as emission signals that we see from 3D explosions of these models. So starting off, core collapse supernovae, right? So we expect that there's about 3 per century for a Milky Way type galaxy. We know that they're more numerous than thermonuclear supernovae, about 4 times. They liberate a ton of neutrinos. They have kinetic energies on the order of about 1 beta. And then we believe that they're the end phases of massive stars about 8 times more massive than the sun. So that's kind of our working picture for them. So understanding core collapse supernovae is really important for different areas of astronomy. And so one of the main areas, or big areas, I should say, is galactic chemical evolution. So they have impact on the nucleosynthesis. They can feed future generations of stars. And they also have an impact on the compact object formation, right? So they're thought to produce stellar mass black holes and the neutron stars that we observe through in-spirals and so on. And so in doing so, this has really big implications for multi-messenger astronomy. And so they can produce gravitational wave emission, either through the collapse or the late explosion, or during the explosion phase, the pre-explosion phase, as well as with the compact objects that they form. Of course, the neutron stars can themselves in-spiral and produce emission, as well as the stellar mass black holes. They also produce neutrinos, and this is something that we can observe, and this is something that with these models, we can actually combine with the gravitational wave emission to find out unique information about the progenitor that we wouldn't otherwise be able to do. So this is something that's really interesting us in terms of core collapse, and that's why we try to utilize models to kind of get at these questions. So we're now kind of in the era 3D core collapse supernova simulations. And so here I have some of my favorite volume renderings of core collapse supernova explosions. So what we're showing in the center of most of these images is the protoneutron star during explosion. The quantity that's being shown here is the entropy. And so entropy is a good diagnostic to kind of follow the shock morphology. And so different colors correspond to different levels of entropy. So higher entropy, usually in the extended regions. And so these are different works that are going on. Some of these have different choices of input physics. Some have MHD. So the top right is work by Philip Mosta, and that's actually a rotating progenitor, rapidly rotating MHD model. But all of these have different aspects of physics that makes them really challenging to model. And so in a lot of cases, you have to sort of compromise on the fidelity of one particular piece of physics in order to afford to simulate the model because they're so computationally intensive. Okay, so the problem, right? So One of the problems that we see with these simulations is that you'll run them, you'll use the best physics that you can, the most sophisticated neutrino transport that's available, high spatial resolution and so on. But you'll get simulations like on the right, where I'm showing a 3D simulation of a 20 solar mass model produced by someone on this call, actually, that's actually failing to explode. So you have the protoneutron star in the middle, you have the shock initially exceed outward, and then it stalls, and then it falls back down. You have some sort of oscillation at late times. This is something called the standing accretion shock instability. But overall, the model fails to reach shock revival during the time of the simulation. So the simulation event is eventually stopped. And so now we have this question as to, what is the reason that we're not able to produce these robust explosions? For this particular progenitor, we expect it to explode. So what are the main factors that's sort of preventing us from doing that? So typically what happens is people will take a 1D stellar evolution model from, like, say, Mesa or Kepler, evolve it all the way to core collapse. Then they'll map it over into their 2D and their 3D hydrodynamics codes. You can use Castro, Flash, or some examples of explosion simulation codes. The one on the right was actually produced using Flash. And when you do this, you take this 1D prescription, you map it into 3D, and one of the issues that typically arises is that you have no information about the non-radial convective properties. And so this is something that could potentially be a missing ingredient for your 3D explosion model. And so this is something that people have started to think about. So getting into more detail of what are potential solutions to this. So there's general relativity. So GR hydro is really hard to do. And so typically you can make some sort of approximation to your gravitational potential to sort of fake it and get something that's more computationally feasible. So that's something that's done. It leads to more compact protoneutron stars, which eventually leads to larger neutrino luminosities, which means I guess easier explosions. So that's one possible area. The treatment of neutrino transport. And so neutrino transport is really hard to do in these simulations. And so there's different levels of approximation. And so the level at which you approximate it, whether, I guess for one example, whether or not you follow the angle dependence of the neutrino transport can make a big difference in whether or not the model explodes. It changes the overall effective neutrino heating rate. It can significantly alter the evolution of the shock. One of the main things, though, that we wanted to focus on was the initial 1D models. And so, like I said, if you take a 1D spherically symmetric model from your stellar evolution code, you actually miss a lot of information about the non-radial convective velocity flow, and that can actually change the evolution of explosion. So that's something that I want to focus on for the remainder of the talk. So one of the first works to sort of look at the initial model near collapse, so in the context of the explosion mechanism, was a work in 2015 by Sean Couch and collaborators. And what they did was they took this 1D spherically symmetric Mesa model and they mapped it for about 155 seconds before collapse into Flash and evolved it in 3D, in a 3D octant. And so here we're showing an XY slice of this model. We're looking at the radial velocity. So we see the iron core, very low radial velocity activity in the middle, and then outside of that's the silicon shell region. And so as we moved left to right in time, the last slice that they have of their model, you see that you can get radial velocity speeds up to about a couple hundred kilometers per second. So this non-radial flow can have significant implications for when that model is then collapsed and then exploded in a 3D simulation. And so this is sort of begging the question, how can we capture this in 1D simulations or 3D simulations necessary to get an accurate picture of what the progenitor looks like before collapse? And so they took this model and they exploded it, right? Because they wanted to test this. So they exploited the 3D initial octant model. So they followed it all the way down to bounce and then followed it through with a simplified explosion. And they also took that same model, but they angle averaged it at collapse and then put it into their core collapse code. So something that's typically done in the field. And then that's what other people do. They don't usually inform with a 3D model, but they still wanted a comparison between the non-radial perturbations and the the radial ones. And so they found for their 3D model, it actually explodes earlier and more energetically. And that's what I'm showing here. On the x-axis, I have bounce time. So the time post-bounce before the core bounces or after the core bounces. And on the y-axis, we have the angle average shock radius. And so the cyan line showing that the shock runaway occurs earlier and more energetically. And so this is kind of pointing to that same question or solution that we suggested earlier is that if you use these 3D models, they get you a more accurate description of what the, the situation is before core collapse that then leads to a successful explosion in most cases. So there's a similar work by Bernard's group, Bernard Muller in 2017, where they took an 18 solar mass progenitor and they actually evolved it, excuse me, in 4 pi instead of the octet symmetry. And on the left, then they use this progenitor as input for their core collapse simulation. And on the left here, I have the 3D initial progenitor. Here we're showing a ZY slice of entropy. So this is trying to trace the shock radius and morphology. And so the 3D progenitor on the left, very asymmetric explosion, a shock at large radius. And on the right, we have the 1D initial progenitor, where the shock is at much smaller radii. The scale are actually different between these two. And then the explosion's actually failing. And so again, showing the same sort of qualitative behavior, these 3D initial progenitors sort of lead to more robust explosions. So very quickly, some of the few ways that they can actually influence the explosion, because we want to be sort of specific about this, is that they found that when you have Mach numbers in the progenitor inside the different burning shells, that those can scale as density fluctuations that could be favorable for explosion. And so the larger Mach number you have in your progenitor model, the larger the density fluctuation, the larger or the more likely that you might be able to produce explosions. And then so they also found that the non-radial flow structure in the post-shock region can actually increase the mass in the gain region, which indirectly increases the neutrino heating rate. And then Sean Couch in 2014 and in 2015 as well sound very, they found very similar behavior when they looked at the kinetic energy spectra for their 3D models. And so that kind of leads us into what we wanted to study, right? And so we wanted to kind of extend on these works and see if we could look at a 15 solar mass model, look between 2D and 3D, extend it out to evolve it longer, so kind of relax the approximation that Couch did in 2015, and then some of the work that Bernhard did, and explore sort of the effects of resolution and dimensionality. And so that's what we did with Flash. So we used MESA, the 1D stellar evolution code, to run our model to about 7 minutes before core collapse, and then we mapped it over to Flash to perform our multi-D simulations and kind of quantify the differences that we saw. So on the right is just I guess kind of a standard profile plot that we have of our initial model. On the x-axis is Lagrangian mass coordinate. So for 0, that means you're at the center of the star, and then you move outward in terms of enclosed mass for the stellar model. And then you have entropy, specific electron fraction, and density on the bottom. So this model is not particularly interesting, and that's kind of what we were going for. We're trying to go for a pretty typical 15 solar mass model. Just kind of showing that here for completeness. So this is what we found. So we ran this model for 7 minutes before iron core collapse in multiple dimensions. We did 2D, 3D. And so this is the result of the 3D simulation that we ran, our 4 pi 3D simulation. So this is showing the last, I want to say 50 or 60 seconds of the simulation. Here we're visualizing the volume rendering of the magnitude of the velocity field. In the center, we're showing an iso contour that follows the iron core. And then above that, the purple flow is about at a Gaussian peak of about 300 kilometers per second. And then the more extended white convection is showing the slower speed at about 100 kilometers per second. And so this entire region is showing the oxygen shell region. And so we're noticing a large range of convective scales that are being observed, and we're also seeing very asymmetric flow, all of which can points to favorable conditions for an explosion. And so this was something we're really excited to see with this 3D model. So looking at it more quantitatively, we took this here, we're showing an XY slice of this same model at a few seconds before iron core collapse actually is initiated. We're looking at the radial velocity. And so in the middle, we see the iron core. Above that is that kind of torus is the silicon shell burning. So very large plus or minus radial velocity of a couple hundred seconds, or a couple hundred kilometers per second. And outside of that is the oxygen shell region, showing that asymmetric flow again. We're actually not showing the full extent of the oxygen shell in this, but these are all very large speeds, so similar to what Sean Couch found in 2015. So very, very similar conditions. And then it's a bit similar, but weaker convection to what Bernard's group found in their 18 solar mass model. So we can kind of quantify that a bit further, right? And so we can use our 3D models to kind of see how do these compare to our 1D MESA models. So say you don't have, in the absence of a 3D progenitor, how good is the MESA model, right? And so that's what we wanted to try and answer with this. And so on the x-axis, we see the Lagrangian mass coordinate again. On the top panel is the convective velocity speed, the bottom panel, the angle average Mach number. And so I'll point your attention to the green line, which is the MESA model, the 1D spherically symmetric model. And so the inner region is the silicon shell. And so this first sort of curve around 1.6 solar masses, that's the silicon shell region. In some cases, you can get the MESA model to match the speeds and the Mach number inside the silicon shell region for a given combination of resolution or dimensionality. But in all cases, that second curved region, which corresponds to the oxygen shell region, the extent of that oxygen shell region is smaller, so it goes out. It doesn't go out as far in mass coordinates, so it has a smaller radial extent, and it also doesn't match the convective velocity speeds. It actually underpredicts it by a few factors, I think a factor of 4 or so. And so this is something that, if you're using these 1D input for your 3D explosion simulations, this is something that could potentially have an impact on whether or not your model explodes. And so it's something that definitely we want to point out, it's people that sort of take into consideration, even in the absence of 3D progenitors. So kind of motivating us to kind of move, what we learned from this 15 solar mass model, we wanted to take that to sort of the next step and see, what does it look like across a range of initial progenitor masses? And so kind of motivating that, so on the right here, we have initial zero age main sequence mass on the x-axis, and on the y-axis, we have Mach number for the silicon and oxygen shell region. And so these are predictions from 1D Kepler models from Collins et al. In 2017. And it's very stochastic, right? And so there might be some sort of behavior that you can maybe fit a line to beyond about, I guess, 28 solar masses, 27 solar masses. But below that, you can basically get almost any Mach number within this range inside the convective shells. And so we wanted to see if these trends followed in 3D, right? And so we knew what our 15 solar mass model looked like. We could plot it on this plot. But this is kind of what motivated us to sort of hopefully start looking at what the progenitor landscape actually looks like for 3D simulations. In addition to that, when we were choosing our next models, so we wanted to, perform in this next study, we wanted a handful of models, 3D simulations. We wanted to evolve them longer, so 10 minutes here, capture more convective turnover times. We wanted something where we had different initial masses. But in addition to that, we wanted to explore a range of what's called compactness, which is effectively a measure of the depth of the gravitational potential. And so the reason we're interested in that is because it's argued that stars that have very high compactness could be potential to undergo failed explosions, right? And so on the right here, I'm showing x-axis is the compactness value, y-axis is the black hole formation time. So in the event that a high compactness star failed to explode, that would be the time that it would actually take to form this black hole. So the progenitors that we're using span a nice range here in this sort of landscape that we're trying to probe. And so this is something that we wanted to do with these new set of models. And we also want to explore things like energy transport and just the bulk convective properties as well, and then compare them back to the 1D works and see how they stack. So we have some preliminary results from this. So we already ran our 14 solar mass model, and so this is about 300 seconds before collapse. Again, we're showing the iron core denoted by the cyan kind of contour in the middle, and then we have the oxygen shell velocity being rendered here. It's a much slower convective speeds here in this particular model, and then the silicon shell is actually very thin. And doesn't become very convectively active until very near collapse. And so we're starting to kind of analyze these data and see how they compare. But already between the 14 and the 15 solar mass model from our previous work, we can see a large difference in their behavior. So you can compare that, right? So on the right here now we have the Lagrangian mass coordinate. Y-axis again is the Mach number. So the orange line is this new 14 solar mass model. And then the blue line is the 15 solar mass model from our previous work. And so we see that in the oxygen shell, it's somewhat similar. The 14 solar mass model is a bit weaker or has a bit lower Mach number, which would imply a smaller density fluctuation. And in the silicon shell, like I say, that it's very weak silicon convection in the 14 solar mass model. So already we're seeing qualitative differences between these models, which is what we expect. But it's also allowing us to sort of survey this landscape. So yeah, so then one of the next models that we have is the 20 solar mass model, which I'm showing here. This is an XY slice of the 20 solar mass model, 365 seconds from the start of the simulation, which is I think about 200 or 300 seconds before core collapse. We're showing the radial Mach number. At least I think that's what's plotted. I have the pictures from Zoom over the axis, but it's large and it's very asymmetric, and that's something that's exciting that we're excited about for this model, is that we're seeing now very large Mach numbers, which could have very large implications for the gravitational wave emission and so on at later times. And so in the middle there, we have the very low convective activity iron core, a thin silicon shell, again, on top of that, and then these very large asymmetric flows that are also occurring at a wide range of physical scales in this model. So this is a model that we're currently running and that we're excited about. And we're trying to quantify, see things like different energy transport and so on inside the model. And so something we're excited about. So the last thing I'll talk about briefly is using these progenitor models as input for core collapse supernova explosion simulations. So what we did was we took our 15 solar mass model from our previous study. We evolved it in 1, 2, and 3D simulations of core collapse explosions using Flash. And so we use the Flash core collapse simulation framework. We use our multidimensional neutrino transport called N1. We have all the bells and whistles, velocity dependence and so on. And so this is something that we're excited about. And on the right, we have the post bounce time. And on the y-axis, we have the annual average shock radius. And so the 1D and the 2D models all explode. The orange line that's looking like it's going to explode is the 3D simulation that we're running. We're running this on Theta right now. It's actually actively running as we speak. And so this is all preliminary, but it's looking like we're going to observe shock revival in this simulation. So it's something that we're excited and we're following this out. And so as we're doing this, we're sort of trying to observe, what is the explosion morphology look like? And so here I'm showing in the XY axis that 3D model, for some 100 milliseconds post bounce or so, showing the entropy again. And we can see that the shock is starting to overall expand. And it does look like it's about to achieve explosion and, shock runaway. But this is something we're following right now, and it's something we're interested in to see the impact on the gravitational wave signal, but also the neutrino emission signal is something that we're interested in as well. So we're actively analyzing these data right now. So one of the last things I'll mention is the gravitational wave emission spectra from this model. So I have post bounce time again on the bottom, and then I have the gravitational wave strain multiplied by distance on the top for the 3D model and on the bottom for the 2D simulations, where one color denotes a 1D initial progenitor and then the other color denotes the 2D progenitor. So one of the main things that you'll see is that the 2D progenitor qualitatively affects the emission signal. And so this is something that's very interesting. In both of these models, we see prompt gravitational wave emission from prompt convection. Then we see some emission at late times due to some oscillation in the 2D simulation. So these are things that we're actively analyzing. For the 3D model, the emission signal is quite weak, but it gives us a basis for what we expect for non-rotating 3D models. And so that's something we're excited to sort of quantify with this work. So yeah, so today I talked about how we're using 2D and 3D models to accurately capture what we expect convection to look like near core collapse. I talked about how we're looking at the landscape of progenitors across different initial masses to kind of get an idea of how this changes for different initial conditions. And beyond that, I talked a bit about how we use these models, these 3D input, to produce high fidelity, multidimensional predictions for different multi-messenger signals. So with that, I'll be happy to answer any questions, and thank you.
Great, thanks, Carl. Yeah, we'll open up the floor to questions. So please use the raise hand feature in the chat. Okay, Evan.
Thanks. Yeah, I just had a question about your first point on sort of comparing the need to do 3D simulations even in the progenitor stage before you get to the explosion. Particularly, like it was a really nice plot with the oxygen shell comparison. And I'm wondering, is that something you see as kind of an inherently 3D phenomenon, that we've already reached the stage where 1D just can't capture the physics, or is there just something that's missing so far from the 1D models that maybe you could rescue them so that you don't have to spend all those extra resources at that stage?
I think it's a little bit of both. I think that one might be able to use the 3D models to inform the convective profiles for the 1D models. So if it's like, increasing the convective efficiency by some factor, which means modifying MLT or something, which I don't want to touch, but I'll say that I do think that a lot of these things that we're seeing are inherently 3D. And so that's something that we hope to at least inform people. Even if people don't want to run the 3D explosion, we'll take an angle average, we'll pass you the 1D profile. And I think that's still better than what's being done.
Awesome.
Yeah. Do we have any more questions? Okay, John? John? Oh.
Sorry.
Yeah, that's okay.
I was wondering whether the pre-supernova convection could influence the scale of the convection during the explosion and thereby affect the kick given to a neutron star.
Yeah, that's a good question. I do think that it will affect the scale somewhat. I think that it won't have a very large impact though. I think it has more of an impact on things because what I've seen in the literature is that it's in the post-shock region that it's sort of affecting the mass inside the gain region, which I can imagine will affect sort of the convective efficiency inside the gain region. But I don't think in terms of the scales, I think that's going to be set by the resolution of the simulation and the overall energy of the explosion. But I think otherwise the scales should be somewhat similar. But I do think it will, I do think that you can have an impact on the neutron star kick depending on how asymmetric the explosion is, which can come from the progenitor.
So we have time for one more question. Please raise your hand or I'll ask a question. Do your models take into account rotation? And if so, how do you expect that to change things?
No, these models don't. I do think the rotation is a very important part of it, even in the slow rotating cases. I think that in terms of the pre-supernova perturbations that we're seeing, I think that those will be only mildly affected. But I think what'll be more interested is how those perturbations are amplified during the collapse phase for a rotating model. And then I also think that the rotating model will have a much larger impact on the multi-messenger signals that are produced after bounce. And so a
Okay.
3D rotating collapsing model, once that explodes, it will produce a different type of gravitational wave emission than a rotating 1D model.
And also the shape of the explosion, right? Because you kind of
Yeah.
expect more like bipolar.
Exactly, yeah. So depending on the degree of the rotation, it could produce some sort of bipolar, and then that would significantly alter them.
Cool. Well, let's all thank Carl again. And we'll move on to the next talk. I'll let Marion get on, do that.
Okay, yeah. Thank you, Anna, and thank you, Carl. So it's my pleasure to introduce our next speaker, Ethan Nadler. Ethan is a graduate student at Stanford, and he's planning to defend this year. Currently, he's working with Risa Wexler on galaxy formation and dark matter physics with a focus on dwarf galaxies. Before Stanford, he was at UCSB, where he worked with Peng O. And so, like I said, his main interest is on using small scale structure as a tool to understand dark matter physics. And more generally, Ethan's interested in simulations, analytic descriptions of structure formation, and he's an active member of the DES, LSST, and SAGA surveys. So Ethan, the floor is yours if you'd like to get started.
Great, thanks. Let's see. So can you see my screen and hear me?
Yep, it looks great.
Okay, awesome. So yeah, thanks for having me. Thanks for the introduction. Yeah, hi everyone, I'm Ethan. I'm really excited to tell you about some of the work we've been doing over the last few years in Risa Wexler's group, also in the Dark Energy Survey, using ultra-faint dwarf galaxies as a tool to understand galaxy formation and dark matter physics. So a lot of what I'll talk about is on the dark matter side, and I kind of like to start with this slide that shows like a landscape of particle candidates for the dark matter particle. So of course we know, from a cosmological perspective that dark matter is cold and collisionless on large scales, but really that's it has to be an effective description, and we know that at a microphysical level that description must break down, and there have to be unique signatures associated with the physics of the dark matter particle. And of course, we have no idea what dark matter is, right? So there are many candidates, dark matter candidates, each of which has its own unique physics associated with it. So I find this kind of daunting at first glance. Obviously, there are many microphysical possibilities for what the dark matter particle can be. And it's difficult, to build like a dedicated experiment to search for each of these types of physics. But from a cosmological perspective, I think there's actually kind of a nice organizing principle that allows us to kind of differentiate dark matter models. So this plot is from a very nice review paper by Buckley and Peter. What it shows is many of the models that I showed you on the previous slide in this parameter space of coupling of the dark matter to the standard model on the x-axis. And on the y-axis is what I'll call the minimum halo mass. So this is the mass of the smallest gravitationally bound dark matter halo that can form in a given dark matter model. And so the point is that, if you look at the vertical scale here, the dark matter models are often, very effectively differentiated by this minimum halo mass. So another way of saying this is that the microphysical properties of dark matter generically affect structure formation on very small cosmological scales. So, maybe a more familiar way for cosmologists to think about this is in terms of the matter power spectrum. So, this very, very famous plot shows essentially the clustering of matter as a function of cosmological scale or wave number k, with larger scales to the left here, measured, of course, very precisely by the cosmic microwave background. And then as we move towards progressively smaller scales, there are, precise measurements of this power spectrum using galaxy clustering, weak gravitational lensing, Lyman alpha forests, and so on. And so the question is, if we try to understand what this power spectrum is doing on extremely small scales, so physical scales smaller than roughly a megaparsec, depending on the type of microphysics associated with dark matter, this power spectrum generically deviates from that of a cold collisionless dark matter model. So these small scales, must contain information about dark matter physics at some scale, and so we're really compelled to understand those scales. And I think a very natural question in this regard, and something that I've been working on a lot, is the question of what is the luminous content of these extremely small dark matter halos that cluster on these length scales. So to this end, right, I mean, we know, of course, there's a really rich body of evidence that suggests that more luminous galaxies live in more massive halos. So of course, turning that around, right, what we want to do to probe extremely small dark matter halos is to search for extremely faint galaxies. So this is a plot of every known galaxy in the universe, in the local universe, out to a distance of 6 megaparsecs, with the brightness of the galaxy on the y-axis. So dimmer systems are towards the bottom here. And what you can see is just by eye, is a very clear kind of locus of detectability, such that we can only measure the existence of the faintest galaxies nearby. And in particular, we can only detect, so-called ultra-faint dwarf galaxies within the virial radius of the Milky Way halo, at least for now. So these ultra-faint satellite galaxies of the Milky Way occupy the smallest luminous dark matter halos, and so we're really, compelled to understand their population statistics to in turn understand the formation of these extremely small halos. So luckily, this is a really actually very exciting time to do this kind of science. So observations of the Milky Way's satellite galaxy population have really drastically improved in recent years. So roughly after Sloan roughly 30 Milky Way satellite galaxies were known, and then in the last 10 years or so, deep photometry by the Dark Energy Survey, other dark energy camera surveys, and other surveys have really increased the known number of satellites. So again, doubling it. The population of known Milky Way satellite galaxies is now up to 60 or so. And there are a few exciting things. So one is that DES, of course, has surveyed the sky in the region, in the vicinity of the Large and Small Magellanic Clouds. And in fact, has detected many ultra-faint satellite galaxies in this region. In fact, more than you would expect if galaxies were isotropically distributed on the sky. So this has actually been interpreted as evidence for the existence of satellites of the Large Magellanic Cloud accreting into the Milky Way. And I'll come back to this later. Another exciting qualitative thing here is that really deep surveys like HSC that survey very small regions of the sky for now consistently detect fainter galaxies at large distances than other surveys can find nearby. And so from an purely empirical standpoint, what this means is that the current census of satellite galaxies is highly incomplete. And we expect to detect many more of them with surveys facilities like the Vera Rubin Observatory, and I'll come back to this as well. Okay, so given these amazing observations, we have to ask, right, like, is there a missing satellites problem? That's kind of a crude way of putting it, based on kind of the historical, how it's been talked about in the literature. And if you read kind of the papers from the last 5 years or so, the consensus is that there is no missing satellites problem after correcting for the fact that our current observations are incomplete. And if you perform some reasonable extrapolation of like a stellar mass halo mass relation into this ultra faint regime, or if you run a hydrodynamic simulation, although those can't, the resolution of those doesn't really allow probing the ultra faints, at least not in kind of a statistical sense. So the important thing is that this consistency, right, this claim that there's no missing satellites problem has generally only been demonstrated at fixed modeling assumptions. So for example, fixed assumptions about subgrid physics in hydro simulations, or in the case of empirical modeling, fixed assumptions about extrapolations of the stellar mass halo mass relation and so on. And moreover, it's only been demonstrated usually for the brightest half of the Milky Way satellite population, usually the classical satellite galaxies and those discovered by Sloan. So not including that population discovered by DES. So this kind of situation is what led us to develop the modeling framework that I'll be telling you about. I don't have time to go into detail on every piece here, but broadly the idea behind what we do is we run very high resolution resimulations, cosmological zoom-in simulations of halos that are specifically selected to resemble the Milky Way system, both in terms of its formation history, using what we've learned about that from Gaia, and in terms of the existence of a realistic Large Magellanic Cloud-like system that has fallen into the Milky Way recently and brings its own population of subhalos into the Milky Way. So we combine this with an empirical model for the galaxy halo connection that crucially is parametric in the sense that, as I was saying earlier, we don't understand fully the details of the connection between dwarf galaxies and their dark matter halos. So it's really key to kind of parameterize that relationship in a way that can be marginalized over in a statistical sense. And I'll come back to that. A large part of this effort has been combining these predictions with essentially selection functions derived from the photometry that say for a given satellite galaxy at a certain position on the sky with a certain luminosity and size, what is the probability that it will actually be detected in photometric data? So these selection functions are directly constrained by the imaging data, and they allow us to form an apples-to-apples comparison between our predictions and the data, which can then be fit for in a statistical sense using like an MCMC approach. So I want to go into a little more detail just on the empirical modeling here, since I think it's particularly important. As I said, we don't know what the connection between ultra-faint dwarf galaxies and their dark matter halos is, but we can kind of parameterize it in a reasonable way that is then flexible enough to be kind of fit for. So just to give you some examples, what we can do, there's this idea of abundance matching, which is essentially the idea that more luminous galaxies more massive dark matter halos host more luminous galaxies. And so we can extrapolate that into the regime of ultra-faint galaxies, leaving things like the slope of the luminosity function for these satellite galaxies and the amount of scatter in that relationship free, and even the fraction of dark matter halos, of these small dark matter halos that host dwarf galaxies. So these are all things that are fit for in our statistical inference using this, the observed satellite population. Another really important aspect of the work we've done is to account for the sizes of small satellite galaxies. And this is actually extremely important because observationally, satellite detectability is a very strong function of surface brightness, but it's not just a function of satellite luminosity. So similarly there, you can kind of extrapolate a relationship between the size of a satellite galaxy and the size of its dark matter halo into this regime of these small dwarf galaxies and then fit for the parameters governing that relationship. So just to give you a sense of the results, after performing the statistical inference, the first thing is that, using a pure CDM model, so using CDM simulations, you can obtain a good fit to the data. Importantly, a really key finding is that the existence of a realistic large Magellanic Cloud-like system is absolutely required to fit the observed satellite population. So an LMC with a peak halo mass of roughly 10 to the 11 solar masses that fell into the Milky Way within the last 2 gigayears and is now at the correct distance from us is required to fit the data. And this is because it brings with it the population of its own satellite galaxies that causes distinct anisotropy in the observed satellite population, as I was telling you about earlier. And I think the really remarkable thing about this is that based on this work we've done, we predict that current observations should detect roughly 6, with some error bar LMC satellite galaxies, and that's consistent with the number of LMC satellites that have been inferred based on their proper motions from Gaia. So that's a nice sign that our model is doing something consistent here. Okay, so I told you earlier that we can parameterize and fit for what I'll call the galaxy occupation fraction. So this is the fraction of these low mass dark matter halos that host an observable satellite galaxy. So again, the posterior from our fit here is shown in blue. The really remarkable thing is that the data is consistent with every halo hosting an observable galaxy, essentially down to the resolution limit of our simulations. So another way of saying this is that there's no evidence from the current data for a cutoff in galaxy formation in these very small halos due to either reionization or dark matter physics. So the data are consistent with every halo hosting a galaxy. So just to put that in a bit of perspective in terms of galaxy formation theory, there's this idea of the atomic cooling limit, which says that halos below some critical mass, roughly 10 to the 8 solar masses or so, can't efficiently cool their atomic hydrogen which should inhibit the efficiency of star and galaxy formation in those systems. Right, so we see that we're kind of right up against that atomic cooling limit already with the current observations. But what we have detected, is really evidence for the inefficiency of star formation in these small systems. So even though every single one of these small halos hosts a galaxy, the slope of the relationship between stellar mass and halo mass is actually quite steep, right? Such that star formation has been extremely suppressed in these small systems. And that's, of course, consistent with our understanding of reionization, effectively shutting down gas accretion and star formation in these very small halos. So I should say that it's very difficult to detect galaxies, or even really to define what a galaxy means for systems that have fewer than 100 stars or so. And we're kind of right up against that detectability threshold already with current observations. So these techniques, with future observations, the statistical precision of these measurements in the regime of 10 to the 8 solar masses and up will increase, but it's very hard to push below halo masses of 10 to the 7 or so using the luminous tracers alone. So a question that I often get asked, which is very important, is is the Milky Way representative, right? Are these inferences that we're drawing about the galaxy halo connection or about dark matter physics representative of what we should expect, right? Like cosmologically. So to this end, it's actually really key to note that from the observational side, these surveys of Milky Way-like satellite systems in the low redshift universe are rapidly advancing. So one example of this is that of the Saga survey, which has now measured the luminosity functions of 36 Milky Way-like systems down to a luminosity of roughly 10 to the 6 solar masses, so not all the way to the ultra-faint regime, but still low enough to get roughly 5 to even 10 satellites per system. And so the kind of remarkable thing is that our predictions, right, constrained only by the Milky Way satellite data, are actually consistent with the distribution of satellite luminosity functions measured by Saga. And this data is going to continue to improve in precision. This should reach 100 Milky Way analog luminosity functions within the next year. So there's obviously a lot to do there. I also want to note that these observations of ultrafaints in the Milky Way are really key for our understanding of galaxy formation at high redshifts. This is because the progenitors of these extremely faint dwarf galaxies are not directly observable at high redshift. In fact, they won't be even by surveys like JWST. So what this means is that in order to kind of reconstruct what the high redshift luminosity function was in this extremely faint regime, we have to use these tracers in the local universe as tools to kind of work backwards, right, and infer that luminosity function. And in fact, this has been done using the brightest Milky Way satellites. So if you use the roughly 10 classical satellite galaxies, and you combine those with abundance matching constraints, you can already kind of have some constraining power over the slope of the galaxy luminosity function at high redshifts for these very faint systems. So obviously these constraints will improve quite a bit, right, as we use more Milky Way satellite galaxies and use these new observations. And this has many implications, for example, in terms of the kind of contribution to the reionization budget of the universe from these very faint galaxies. Okay, good. So with that setup, I'll tell you about the work we've been doing to kind of infer dark matter physics from this work. So the basic idea is that in a CDM model, you form halos essentially down to the free streaming scale in that model, which is extremely small of order an Earth mass halo. But if dark matter physics manifests on these length scales, for example, in the case of warm dark matter kind of suppressing halo formation due to free streaming, you can suppress the abundance of halos right on the kind of mass scales that we're observing using these satellite galaxies, right? So by counting the satellites and making some, for a given guess about how the subhalo mass function is suppressed in a dark matter model, you can actually place constraints on these non-CDM scenarios. So we've set up a framework to do this, which is kind of broken down into these three pieces. So just kind of schematically, given an assumption about dark matter physics, you can calculate what I'll call the transfer function. So the ratio of the linear matter power spectrum relative to that in CDM. If you feed that into one of these numerical simulations, you can predict how strongly the subhalo mass function is suppressed relative to CDM. And then that is used as input, right, in a prediction for the satellite luminosity function. So in these models I'm showing you, essentially the suppression is strong enough such that you underpredict the number of ultra-faint satellite galaxies at the lowest luminosities, right? And so these models are ruled out by the current observations. So the kind of model independent way of stating the result is that current satellite observations are sensitive to roughly 25% suppression in subhalo abundance relative to CDM. And then in the context of specific models, right, this places constraints on the parameters governing the microphysics. So just to give an example, right, for dark matter that is produced thermally, such that it is warm and free streams on large scales, this framework yields a lower limit of 6.5 keV on the mass of the warm dark matter particle at 95% confidence. And this is very comparable to limits that have been set by, for example, the Lyman alpha forest or strong gravitational lensing, or even using stellar stream perturbations, of course, with completely distinct systematics, which is a good thing, right? These different techniques are giving us the same answer. The thing I find compelling about this is, this really constrains a wide variety of dark matter particle properties essentially at once. So this is kind of the opposite from a theoretical perspective of searching under a lamppost, right? And I'll walk you through some of the various things that are constrained. Okay, so just to give a little more detail on the warm dark matter constraints, what can be done using this thermal relic warm dark matter constraint is to work out, right, in the context of a specific dark matter scenario, such as resonantly produced sterile neutrino warm dark matter, what are the constraints on the microphysical properties governing that model? So this plot shows the mass of the resonantly produced sterile neutrino on the x-axis, its mixing angle with the standard model on the y-axis. And what you can see is that these Milky Way satellite observations, rule out really large regions of this parameter space. In particular, they, very robustly rule out the interpretation of this 3.5 keV X-ray line from galaxy clusters as a sterile neutrino annihilation. Okay, so I want to briefly mention fuzzy dark matter because it's, it's quite has gotten a lot of interest lately. So the idea here is that if the dark matter particle is so light, such that its de Broglie wavelength is of an astrophysical scale, this actually suppresses the formation of small halos, essentially due to quantum interference. And so what this analysis yields is a lower limit on the mass of the fuzzy dark matter particle of roughly 10 to the minus 21 eV, which is again comparable to other small scale structure limits. It's really key to note here that there's quite a bit of uncertainty in predictions for the subhalo mass function in fuzzy dark matter. Essentially, it's very hard to simulate the evolution of the Schrödinger-Poisson equation. But anyhow, using the most conservative estimate of the fuzzy dark matter subhalo mass function, this is the type of lower limit that you get. And again, this informs particle models like ultralight axions. Okay, so this is the example I want to spend the most time on because it was kind of a novel application of these dark matter constraints. So what we considered in this paper with Vera Glusevich and others is dark matter that scatters with protons with a cross section that's large enough to actually suppress the formation of halos on these roughly 10 to the 8 solar mass scales. So in particular, this scattering between dark matter and baryons essentially suppresses power on small scales due to transfer of heat between these two fluids in the early universe. And you can actually analytically estimate the mass of the smallest halo that's allowed to form in such a model by working out the size of the cosmological horizon when the momentum transfer rate between these two fluids is comparable to the Hubble rate. And the other nice thing that we worked out is, if you actually, forward model, right, this scenario using a Boltzmann solver and work out the transfer function, the initial cutoff in the transfer function is extremely similar to that in thermal relic warm dark matter, which allows you to construct a mapping between the constraints in one case and the constraints in the interacting case. So to show you what this looks like, this plot is for the interacting dark matter model. So it shows the mass of the dark matter on the x-axis and its velocity independent cross-section with protons on the y-axis. So you see direct detection constraints, other terrestrial experiments here. So these are, generically kind of very difficult to push to low mass, right? Because just because the energy recoils are so small there. Cosmological constraints help, right? Essentially, they're not inhibited at these low masses. And as you push to smaller scales, you kind of gain in sensitivity. Then the Milky Way satellite analysis improves by several orders of magnitude on these previous constraints, which can be understood in terms of the co-moving scales being probed by these small halos. And just very briefly, I'll mention that what I showed you here was velocity independent scattering, but if you then generalize this to more essentially more general velocity dependent scattering models, this improvement, right, of like 3 orders of magnitude in the velocity independent case improves more, right, in the cases where scattering is enhanced in the early universe, which is nice. Last thing that I want to mention, which is work in progress, is that of self-interacting dark matter, which is often kind of invoked as a solution to the so-called small-scale structure problems. So what we've done is a really kind of systematic study of self-interacting dark matter models using simulations of these Milky Way-like systems. And what we found is that the suppression of the subhalo mass function is actually quite sensitive to the amplitude of the SIDM cross-section at the velocity scale that is set by a subhalo falling into the Milky Way. In particular, a model with like a 1 centimeter squared per gram cross-section there is extremely suppressed in terms of subhalo mass function relative to CDM. So this means that our observations are sensitive to SIDM cross-sections of order 1 centimeter squared per gram and smaller. And if you just take a look at what's actually happening, it's quite interesting. Because of these velocity dependent SIDM interactions, you have really distinctive effects. Like in the CDM case, you have these little tiny subhalos around the LMC that fell in with it. In the SIDM case, you just have none of these, right? So this, in terms of the constraints, is work in progress and should be out pretty soon. Last thing I want to mention, so I did, I noted earlier that a variety of small scale structure, techniques, probes have reached similar sensitivity in terms of these dark matter constraints. But of course, right, what we want to do is jointly model these different small scale structure probes, which is really necessary in order to break degeneracies among dark matter models and to detect non-CDM physics if it's manifesting on these scales. So what I'm doing now with Simon Breyer and others is to combine the constraints from Milky Way satellites and strong gravitational lensing in a parameter space that is essentially, controlling for the fact that those two probes are measuring halo populations at different halo mass and redshift scales. So this is work in progress. Should be out soon. Okay, so this is my last slide. I'll just briefly go through this, and then I'm happy to take questions. So the lack of the cutoff in the abundance of these really faint galaxies near the Milky Way yields strong constraints on a wide variety of dark matter physics, and these constraints will definitely continue to improve as the statistical precision of these subhalo mass function measurements improve. And I think joint modeling of different small scale structure probes is a really important way to think in the future. We're doing this dwarf galaxy and strong lensing analysis, and another thing that I'm very interested in is combining the dwarf galaxy modeling with stellar stream perturbations to kind of further break degeneracies. So I'll stop there. I'm happy to take questions.
Great. Thank you so much, Ethan, for this great talk. I think you established a lot of really helpful links here. So let's go ahead with questions. And Anna has her hand raised.
Hey, Ethan. Thanks for the talk. Yeah, very nice, and very many things to discuss on the dark matter side. But I was thinking, given that there's so much interest here locally at the CFA into understanding theoretically and also observationally what are the kind of lowest mass galaxies that can form, kind of to get your take on where it would be the best place to search for those kind of 100 solar mass galaxies that at least like given your results now, it seems like unless they just kind of immediately disappear, there should be some in that mass range.
Yeah, absolutely. I mean, so definitely, and thanks for the question. So I mean, on the observational side, I should say that like measurements of these ultrafaints outside of the virial radius of the Milky Way are actually also rapidly advancing. So there's work ongoing in DES to detect these things outside of the virial radius of the Milky Way halo, and I think LSST will actually have some sensitivity throughout the local volume. In general, I think it's very difficult to go distant, which is why I think this link to high redshift is a really important way to think, right? Because if there are other signatures in terms of reionization or 21 centimeter or what have you, right, that's like an indirect way to detect those really faint systems. Yeah.
Thank you.
Okay. Any more? Is there another question? If not, I see Sonak. Go ahead.
Hello, Ethan. Thank you very much for that talk. Apologies if I missed this, but in your modeling, do you get any constraints on what the nature of the radial distribution of the satellites ends up being?
Yeah, absolutely. So I didn't, go into the technical details, but like what we do in the fit is to jointly fit the luminosity function, the size, right, the half-light radius distribution, so effectively the surface brightness distribution and the radial distribution of the satellites, right? So the radial distribution, as with the luminosity functions I was showing you, is consistent with the data, and the constraining, essentially the constraints there are on the efficiency of subhalo disruption due to the disk. And that's particularly coming from the radial distribution in the inner, 100 kiloparsecs or so that drive those constraints, right? So it's definitely there, and it's definitely informative and actually quite important, yeah.
All right, thank you.
Okay. I'd like to ask one last question. Well, so you showed this really interesting slide on where we stand from various probes on constraining CDM. Milky Way satellites are now a competitive probe, according to what you showed us. And I guess a big picture question that came up in my mind was, do you expect that to stay that way in this sort of race forward? Do you expect that this Milky Way satellite's methodology will become even more competitive, perhaps the leading probe? Are we on track to achieve that, or what would be needed to do that?
Yeah, so I mean, so I think, like as I said, I think with the kind of statistics offered by surveys like LSST and others, like the constraints will definitely improve. Of course, other techniques are very promising, like 21 centimeter, in principle can do much better in terms of the scales that are being probed. But I think it's like more fruitful to think about it in terms of the complementary things that are being measured by each technique, right? So like the satellites effectively measure the subhalo mass function, right, at redshift 0, which is a different thing than even the subhalo mass function that's being measured, or the halo populations that are being measured by strong lensing, right? And those different things, right? If the dark matter physics manifests in different ways, right, in those different probes, that's really the way to break degeneracies and actually detect something, right? So yeah, I guess I think about it less of a competition and more of like a way to learn specific types of the dark, the phenomenology of the dark matter model. Yeah.
Great. Yeah, thank you for that perspective. So we are well over time, so I think we'll just end here for today. If you'd like to speak to Ethan or Carl, they have schedules, they're opening in their schedules for one-on-one meetings. And thank you all again for attending today.